Welcome to our P.D training video on modified bolus conversion. Before we get started, I want to take a quick minute to define what a modified bolus is within the P.D software. So the way we define a modified bolus is it is simply any structure that is brought in from a TPS or another system, typically via a structure set file, that we then convert into what P.D considers a bolus type part. And once it's a P.D bolus, you can order that bolus. We associate that bolus with a beam. We can define, or we can mill or manufacture alignment crosshairs and holes for fiducial markers into your bolus product. So the modified bolus tool allows us to develop a part in another program, another software, and then bring it into P.D and order it via the dot decimal system. So what we'll see today in this video is we will go through creating this bolus that was created in another treatment planning system. We will convert this into a P.D bolus and make it ready for ordering. Okay, so as you can see, I've already got my patient loaded up. If you're following along with this tutorial, this is the ECT chest wall case provided by dot decimal. So to access the modified bolus features, we're going to go to the bolus wizard. Okay, once we're in the bolus wizard, we need to select the modified bolus from structure. All right, this is going to reduce the options that we need because we're not going to compute dose or anything. We're assuming that this structure came from a TPS. You've already approved and planned with this structure. So all we need to know is what machine do we want to use, because this is going to define the source axis distance and some other parameters that are important for the conversion. And we need to define what beam do we want to use for the conversion process. I said a moment ago when I defined a modified bolus, we're going to associate the modified bolus part with a beam. This allows us to produce alignment crosshairs on the beam and make sure that the conversion process will happen effectively. If you're familiar with the previous version of P.D, you are able to define an angle for the beam. In this version, that's no longer the case since this was created in a treatment planning system. You'll also need to create the beam in the treatment planning system on which you want to convert this. If this part isn't associated with a beam, chances are good that it may not convert properly within the P.D software. So if it's not actually associated with a beam, it's typically not a good candidate for modified bolus conversion. But you may try anyway. In that case, you may want to just produce a beam that is as perpendicular to the bolus as possible in your treatment planning system. Okay, so once we're here in P.D, select your machine, select the beam that you want to use to associate this bolus with, and the beam basically defines the direction from which we're going to convert this part into a bolus. Remember, a bolus in P.D is simply defined as two surfaces, a proximal surface and a distal surface that should be along the patient. Okay, so we're basically going to represent this part as a top surface and a bottom surface. So with that being the case, we can see that there's going to be some limitations in this process. We shouldn't have inverted walls or walls that basically wrap back on themselves. So if you view the P.D help system, you'll find some very good guidelines as to what constitutes a good part to convert into a modified bolus. I'm not going to cover those details in this video today, as the help system does a thorough job of describing those. Instead, what we're going to look at is simply how do we create these parts. So once we've got our beam and our machine selected, we need to now tell P.D what part do I actually want to convert into a bolus. And we can see, well, my structure here that I want to convert is shown, but that's because I turned it on before entering the wizard. It is not the actual selected structure right now. So I need to select that structure. It's called TPS bolus. Now we see that that's the only structure visible. That is the selected structure. So now we can go ahead to the next page where we actually perform the conversion process. And there's really only two options here for our conversion. We need to define how refined do we want the point spacing of these surfaces that we use to convert the bolus. That's our point spacing. And we need to define, do we want to apply any smoothing to the surface when we perform the conversion. All right. Typically, you've already defined this bolus in your treatment planning system. There should hopefully be very little reason to use the smoothing, but it's there if necessary for some cases. So we're going to use just a coarse point spacing here because we just want this to convert fairly quickly for us. So I'm going to change the point spacing to 2 millimeters, and I'm going to generate my bolus. And we'll see the light blue bolus here, or the light blue part, is our new modified bolus, and the dark blue is our original bolus. Your original bolus may be a different color depending on what color it was in your treatment planning system when you imported it into P.D. But we can scroll through and we can see that throughout most of the treatment field there'll be a very good match, because chances are good your bolus is reasonably smooth. We see in some of the corners and some of the stepped areas, well, P.D, remember, wants to represent this as a continuous smooth surface, so these sharp corners are a little more difficult to represent within the P.D system. So you may lose a little fidelity in the sharp corners in favor of smoothness in there, which for electron fields typically may not be a bad thing. What you will notice on occasion, the edges of the bolus may not be perfectly represented. Remember, we used a 2 millimeter grid spacing, so the distance between this end and this end is typically going to be less than that grid spacing. It just means there was no intersections between this and the next point in our grid. So anywhere down, we never intersected the bolus, so we kind of lost that last millimeter or two on the edge of our bolus. Typically that will be outside the treatment field for most cases, so that's typically not going to be an area of concern when you're converting a bolus. So you can scroll through the slices and you can see the quality of the conversion process. If this matches the bolus that you want, then you're done and you can click finish and you're ready to go. All right, we'll do that real quick because that'll bring us back to our tree view, and now we can look in 3D. We can turn this beam off so we can kind of see the part, and we see that we kind of get this very strange looking part here. The reason we see both colors is the surfaces are nearly on top of each other. So depending on whichever one gets rendered first by your graphics card in your computer will determine basically which value or which surface color you see. So when we see this sort of blending, especially in these flat areas, it basically means the surfaces are on top of each other. The computer can't even distinguish which one to show above the other because they are so similar. So that's typically a good sign when we see that sort of flickering and we see that nearly random pattern of colors there. We see on the edges, though, that, well, it's very clear that one is sort of outside the other. On the right here, it's very clear that the dark blue is slightly past the light blue. If we look at the patient side surface, again, we see that mismatch of colors, which tells us that they're pretty much on top of each other. That's really all we can tell from the 3D view. If you need a better view, you need to use some of the 2D views, and we can look at kind of the fitment of the bolus in those other views. And we see that everywhere other than the edges, the bolus match is very good when we don't use any smoothing. If we go back into the bolus wizard and we again select modified bolus, make sure we select our bolus, TPS bolus again, coarse point spacing. Now I want to apply a smoothing real quick, and we'll see that there are 3 options: outside, inside, and average. And these are, again, rolling ball smoothing, just like the patient side surface in constructing a flat top or an optimal thickness bolus. So if we use outside in this case, I'll drop that radius down just a little bit, and we're going to generate bolus. We'll see that this takes quite a bit longer than the option without smoothing. Okay, the rolling ball smoothing is a much more computationally intensive process, so this will take a little bit longer. So while that runs, I'd like to discuss a couple things that we should notice when the part comes out. So right now, we see a very good agreement between the 2 boluses. In fact, on this bottom distal surface, we really can't tell a difference between the 2 surfaces along most of the slices. We're going to see with the rolling ball, however, when we come from the outside, that means the rolling ball is going to be applied outside of the bolus. So it's going to be above and below the bolus. And what we're going to see is we will never protrude into the bolus part. Instead, we're going to protrude outside. That's why the rolling ball is called outside. So we'll notice that in the case of applying this to the outside, we may see that in areas where the beam is, or where the part is very steep relative to the beam direction, like these walls and down here in the bottom, we may see that the rolling ball causes the surface to sort of pull off the original surface a little bit. That can create kind of an interference fit between the bolus and the patient. So if you're applying smoothing, and you be very careful if you're using outside smoothing on watching that patient side surface, because it will create protrusions toward the patient rather than away from the patient, as it was doing in the patient side surface generation for a flat top or an optimized thickness bolus. Okay. The other option we saw for smoothing was inside. So if we choose the inside option, then the rolling ball will be applied to the upper surface from the inside and to the lower surface from the inside. That will cause the surface to pull upward and away from the patient slightly in any deep valleys or areas like that. So if there was an interference fit, if there was a problem with some of the slices, an inside smoothing is typically more appropriate when you're doing a bolus conversion, especially for the patient side surface. Okay, we don't have an option to change it for either surface. In P.D, we just have to choose either outside for both or inside for both. The third smoothing option was the average option. The average option does both the outside and the inside and then simply takes the average position of the two. So it can kind of cause a little bit of smoothing. In cases where there were very deep valleys, we'll still remove some of the valley, but not as much of the valley as if we had done the inside or outside on their own. So sometimes average can be a reasonable blend between using the inside and the outside values. Now with our surface complete, we can go ahead and take a look at how different this appears. So we can finish. And now we can look at the two surfaces and see what the rolling ball smoothing has done to our surface here. So we can see that it kind of pulled away a little bit in some cases. Well, when we go through the slices, we can see that the surface is changing position very rapidly in that third direction. Okay, so that's why the rolling ball smoothing appears to be doing a poor job of fitting, but we need to remember this is a 3D algorithm, so when this applies, it's using all three directions when it does this. It's not simply rolling the ball along a contour. It's also using that third direction to pick that value up. So we can see that, well, for the most part, it does a pretty good job. We can see that in the very steep areas, it will pull away from the wall a little bit due to the rolling ball. And we can see that, well, the patient side surface will pull away a little bit in some cases as well. So as we get steeper and steeper, we see that it tends to pull away just a little bit. These kind of quick turns right here tend to be a little over-exaggerated by the rolling ball smoothing. So we need to take that in mind, or keep that in mind if we're going to apply rolling ball smoothing to these parts. Okay? If you're happy with the surface that you're generated, then you're done and you're ready to go ahead to the order wizard and proceed to order your part within the P.D system.